Linear, linear. It is expansion. This is the next 10 minutes of me just singing that. Okay, anyways. So if you haven't seen the quick little demo where I put a ball through a ring and then got it stuck afterwards and the class laughed at me, check out that video, or the bimetallic rod. But what we're looking at here is linear expansion. And basically the idea is that if you have something like a piece of metal. So here's a piece of metal. Ring! It's like a metal rod. If you heat this metal rod up, this metal rod will expand. As you heat it up, it's going to expand. It's going to, kind of move forward, move this way. Technically, it'll also increase along the radial axis as well. But the whole thing will expand. We call this a linear expansion. And the way a linear expansion works is as follows. The new length of the rod. So this is like the new length of the rod here. This is equal to the original length of the rod, and that original length is the length of the rod at some temperature, okay? So it's like the length of the rod at 23 degrees Celsius. It's at that temperature. But then there is plus, due to this change in temperature, some delta L here, okay? And this is due to the change in the temperature. So we need to analyze if we have a change in temperature, something getting hotter to get larger, or if we cool this down and it shrinks a little bit, how will that delta L influence this? So the way we can rewrite this equation is saying that L, the new length of the rod at some new temperature, equals the original length plus some expansion amount. And the way we get that expansion amount is that delta L here. That delta L is actually equal to the original length of the rod multiplied by some alpha term. This alpha term is the coefficient of linear expansion. So it's the coefficient of linear expansion. And normally, these values of alpha are small. They're like times 10 to the minus 3. They're small values, okay? And then we multiply this by the actual change in temperature. And because this is a change in temperature, it doesn't matter if you measure in degrees Celsius or in Kelvin, because both of those are on that absolute scale, and a change of 1 degree Celsius is a change of 1 Kelvin. So whatever unit you're in, stick with it, except Fahrenheit. That's evil. If we wanted to, we could rewrite this a little bit more succinctly as saying the new length equals L naught multiplied by 1 plus alpha delta T. This is our linear expansion equation. Something that we notice from this linear expansion equation is that if you have a longer object, it is going to expand more than a smaller object, which actually has some large implications. If you have something like a long bridge you're stretching across a river, it might actually be better to break that bridge up into smaller pieces rather than having just one large bridge. And if you actually live in our city of Pittsburgh and you drive across the bridges or walk across them, you might see at some point in time those teeth that interlock. Those are expansion joints there. Those are designed so that in the summer, when the bridge is expanding, those teeth can get a little bit closer together. In the winter, they'll get a little bit farther apart, which always freaked me out as a kid because I was like, I'm going to fall through. You're not going to fall through. Like, they designed the bridge so you couldn't. But the bridge is designed to kind of float on those pieces because if it didn't, if you just had one long piece of bridge, then during the summer when it would expand, what would occur is the asphalt topping on it would start pushing on other pieces and it would begin to buckle. And if you actually look at some other things that do this, like concrete, if they don't put spacings in concrete, you'll actually see some concrete actually like kick up during the summer. It was improperly spaced out because there's some pressure as it expands and it kicks up like this. Likewise, if you had a very long single piece bridge in the wintertime as it cooled down, as it changed temperature, your bridge would contract and you'd start getting large cracks in the asphalt as well. And since we don't want to repair those all the time, it's easier to make smaller sections of bridge that are allowed to expand with the finger joints to allow them to move back and forth. So a really cool thing in terms of engineering to look at this idea. Now, while this is for linear expansion, we can also do this for a volumetric expansion, for a three-dimensional object with some volume. It's an almost identical equation. It's simply that the new volume equals the original volume multiplied by 1 plus beta delta t, where this beta here is the coefficient of volumetric expansion. So it's just another coefficient that we use. It has units of 1 over Celsius or Kelvin in order for those to cancel out and our final values to be in volume. Now, a really cool thing about these values of alpha and beta is that you can actually prove, and one of the intergalactic questions asks you to do this, that beta is approximately, although not exact, but it is approximately equal to 3 times alpha. And if you wanted to prove that, the hint I would give to you is that a volume is nothing more than a length times a width times a height. In our next video, though, we'll be taking a look at using an example of linear expansions to see how we can push this through a problem. But until then, adios, and take it easy.